Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the extrinsic semiconductors. Let's start. By the time you finish this lesson, you will learn the ionizing energy dependency on the dopant atom, common dopants used to make extrinsic semiconductors, and freezing out extrinsic and intrinsic zones. In the first part of the extrinsic semiconductor lecture, I was discussing that for silicon, N-type dopants are normally chosen from group 5 elements and P-type dopants are normally chosen from group 3 elements. It is the time to explain the reason behind these choices. If I dope silicon by an N-type dopant, the donor energy level ED appears on the energy band diagram. If I dope silicon by a P-type dopant, the acceptor energy level EA appears on the energy band diagram. We normally desire to have a small ionizing energies for doped semiconductors. If delta ED and delta EA are small enough, full ionization can take place in a wide range of temperatures. For an N-type semiconductor, if I choose elements from group 6 and above, ED moves down and therefore delta ED increases. For a P-type semiconductor, if I choose elements from the group 2 or less, EA moves up and therefore delta EA increases. So far, you may have ended up to this question that how come we have only one energy level associated with dopants in the energy band diagrams? You may say, didn't Mehdi said when we are not talking about the isolated atoms, we see bands, not energy levels in the energy diagram. This is partially right, and indeed it is a legit question. If you remember the discussion that we had on the energy band diagram in the previous lectures, I said the interatomic distance is important in the formation of the energy bands. For silicon, the dopant concentration is normally in order of 10 to the power of 14 to 10 to the power of 20. If you compare this with the concentration of silicon atoms, which is 5 times 10 to the power of 22 per centimeter cube, you will soon find that for one dopant atom, there are 500 atoms in the extrinsic semiconductor. If the dopant concentration is 10 to the power of 20 per centimeter cube, which is the high end. In other words, between each dopant atom, you can find 500 silicon atoms. Therefore, the interatomic distance between the dopant atoms is very large, and therefore, they cannot fill each other. This is the reason that we have only one energy level associated with the dopant atoms in the energy band diagram of extrinsic semiconductors. Common elements used for N-type doping in silicon include antimony, phosphorus, and arsenic. Common elements used for P-type doping in silicon include boron, aluminum, and gallium. For 4H silicon carbide, nitrogen is commonly used to create an N-type semiconductor, and aluminum and boron to create P-type semiconductor. For gallium nitride, silicon is commonly used to create an N-type semiconductor and magnesium to create P-type. The ionization energies associated with each one of these dopants are given in these energy diagrams. You may pause the video and look at them at your own pace. For example, the ionizing energy in a doped 4H silicon carbide by nitrogen is 77 milli-electron volts. In gallium arsenide, silicon can be used as an impurity to create both the N and P-type semiconductors. This is why silicon is called an amphoteric impurity for gallium arsenide. In the crystal lattice, if silicon is at the gallium site, an N-type semiconductor is created, and if it is on the arsenic side, a P-type semiconductor is created. The concentration of negative charge carriers, electrons in the conduction band at a given temperature can be calculated by using this equation. For a small delta EA and ND being much smaller than NC, N is almost equal to ND at room temperature. By taking this assumption, let's take a look at the concentration of free electrons in the conduction band versus temperature. This diagram is drawn for a doped silicon. The extent from 0 degrees Kelvin to around 80 degrees Kelvin is called the freeze-out zone. From 80 degrees Kelvin to around 425 degrees Kelvin, the concentration of free electrons is flat and equal to the concentration of dopants. This zone is called the extrinsic zone, and this is where we want the semiconductor to operate. Around 425 degrees Kelvin, the concentration of intrinsic charge carriers become comparable with the concentration of dopants. Above this point, the concentration of free electrons increases exponentially. This zone is called the intrinsic zone. The freeze-out and intrinsic zones are not desirable because of several reasons. One of them is that the prediction of the semiconductor behavior becomes very difficult. In this lecture, I talked about the ionization energy dependency on the dopant atom, common dopants used to make extrinsic semiconductors, and freeze-out extrinsic and intrinsic zones. In the next lecture, I will cover the Fermi level and function. Thanks for joining this lecture of Peacademia.